Okay, let's set up this. So let f of x comma y equal x squared y, and define the vector field, capital F arrow, to be equal to the gradient of lowercase f. Then let's find the integral over the curve C of the vector field, capital F dot d vector r, if C is the line segment from the point 2 comma negative 1 to the point 1 comma 3. Okay, so we're given a scalar field or a scalar function of two input variables, little f of x comma y. So it goes by the fancy name scalar field. And if we take the gradient of it, we're supposed to get capital F. So let's write out what capital F is. Let's go ahead and stick the of x comma y here. So we need a partial derivative with respect to x, and we'll have 2xy. Then we take x squared y and partially differentiate with respect to y, and we'll get x squared. All right. Okay, so there's the vector field. That's the vector field that is getting mentioned here that we are to take the integral of. But we also need to parameterize C, which is, in this example, a line segment, write it as a vector function, however. So r of t is equal to 2 minus t. Yeah, change from 2 to 1 is going to be a minus 1. And then comma negative 1 is the starting y value. It grows up to 3, so that'll be a change of 4. So negative 1 plus 4t. We've got t going from 0 to 1. Okay, so then we can write in the, we'll need to compose these two. And again, this notation-wise looks a little funky, but all the books do it. So f of r of t. So we should write 2xy, except we need to replace the x. So we wrote the 2. X gets replaced with 2 minus t, and y gets replaced with this thing, negative 1 plus 4t. Let me write that as 4t minus 1. Comma. Then we have x squared. Okay, so we have 2 minus t, quantity squared. So 2 minus t, quantity squared. Okay, the other thing we're going to need is we're going to need to take r of t and get r prime of t. Okay, so that's going to be negative 1 to differentiate 2 minus t, and then positive 4 to differentiate negative 1 plus 4t. So then when we set up the integral, integral over c of f dot dr, don't forget the arrows, it becomes super critical here. We're going to have the integral from t equals 0 to t equals 1, taken from right over there, of this vector dot that vector. Okay, so let's write this 2 times quantity 2 minus t times quantity 4t minus 1 times, well, the negative 1 as the first component of the other vector, plus 2 minus t quantity squared times 4. This should technically all be in parentheses, so let's do that. Not really worried about that set of parentheses though, dt. And let me spare you the details on all of this stuff, and just say that if you did all the algebra there, you will have an integral from 0 to 1 of 12t squared minus 34t plus 20 dt. And if you evaluate this, you are going to get the number 7. There's obviously some work that was skipped there that can be shown, but let's you can go ahead and do it. It is just a lot of algebra, or maybe just for now just use a little online tool to do that little bit of algebra or something like this. The thing is, we're done with the question, but I'd like to notice some really strange phenomenon that occurs, namely the following. So I'd like to take the parameterization that we were given up here, and I'd like to plug in t equals 0, and I'd like to plug in t equals 1 to see what happens. So please note, if you look at the vector function r, apply input 0, you are going to get 2 comma negative 1, right? Fairly clear by looking at this. Just plug in t as 0. So this is the vector form. What is this? This is the vector version of the initial point. And if you take the function f, the original one up here, it didn't really play much of a role. We just took the gradient of it to get our vector field. If you look at the original function f and you plug in 2 comma negative 1, so those numbers are just coming from here. Let me maybe just draw the arrow one way. So the 2 is coming from there, and the negative 1 is coming from there. And you just evaluate what you get. So x squared y, so 2 squared times negative 1, you get here negative 4. Then let's do the same thing using t equals this other value here, 1. So it just seems like a random computation we're doing, but you'll see where this is headed. Let's see, so if t is 1, 2 minus 1 is 1, and then negative 1 plus 4 times 1, so 4 minus 1 is 3. Okay, well, we kind of knew, right, that it'd be this point anyway. I'm just trying to set it up. So this is the vector version of the final point, right, of the parameterization. So there's this capital C is this line segment that goes from 2, negative 1 to 1, 3. So we're not surprised at the vector that we get here. But if we then take that in point form, 1 comma 3, and feed that into the function f, we get 1 squared times 3, which is the number 3. Yeah? Let's actually write this a little so we've done work that follows standard notation. What we're going to write here looks a little funny notation wise, but f of vector r of 0 we're going to say is going to be the number negative 4. So we just copy this negative 4 right there. Now this we'll do the same here. F of vector r of 1 is equal to 3. Now this is actually a little strange. Okay, this is strange because vector r of 1, this is a vector, and then we're feeding that vector into f, but f takes in a point. F takes in an xy. So, but f wants a point as its input. So this seems a little strange notationally, because it is. Okay, this is notationally, it's a little weird, but we'll go with it. It's just a little bit of that pass back and forth between, how different are vectors and points really. But the thing that I'd like to really notice, then, notice the following. Notice that, so in this new notation, f of vector r of 1 minus f of, let's write that real clean here, f of vector r of 1 minus f of vector r of 0. So let's replace this with the positive 3 that we got, just taking that from right there. Then minus, and then f of r of 0 is negative 4. So, yeah, minus negative 4. Okay, so you get here 3 plus 4, which is 7. And the thing is, this 7 matches with the 7 we have here. This just seems like a random mess of things. I realize that. But here's really the point to make. I'd like to recall, way back from your first calculus class, FTC, the Fundamental Theorem of Calculus, which maybe this wasn't exactly the notation that was used for it in the past, but I'm going to use the following notation because it matches what we're going to do much better. If capital F prime of x is continuous on the closed interval from a to b, then you take a function which happens to be a derivative, right? There's a capital F, which was the original function, and f prime is the derivative. If you have a function which happened to be a derivative of another function, then if you were to integrate that function, okay, capital F prime of x dx, from a to b, you end up with the value being capital F of B minus capital F of A. So we're doing this all without trying to mention the function you're starting with. Notation-wise, this may look a little strange, but it is absolutely accurate as written. Now, what we're going to introduce is a new thing called the fundamental theorem. Of line integrals. Okay, and it says this. Let f be a function of 2 or 3 input variables. So it's like, if I scroll up, it's like the f of x comma y that we have here. Just for instance, something like that. Okay, and then, and suppose capital C is parameterized by a vector function r of t, where t goes between a and b. Then, and to make it sound as much like the fundamental theorem of calculus as possible, then if the gradient of f, so gradient, remember, it's just a bunch of partial derivatives, so that's meant to look a lot like f prime, which is a bunch of derivatives. So if gradient of f is continuous on, previously we had an interval, now we have on capital C, because that's what we're going to integrate over, then the integral over the curve C of the gradient of f dot dr. That's actually what we just did earlier. Our capital F arrow in the example we did was gradient of f, gradient of little f. This is equal to, and we have it right here, at least in our example, it's f of vector r of b minus f of vector r of a. All right, so this, in this box here, is the fundamental theorem of line integrals. And the point is, in our previous example, we see an example of this theorem at work. So we have integral over C of, we'll write it to look more like this, gradient of f dot dr. In our example, this was the number positive 7, and we had f of vector r of 1, so the 1 is b, minus f of r of 0, and our 0 here is a. This entire thing, f of r of 1, was in our example the number 3, and f of r of 0 was in our example the number